Hello everyone, welcome to today's video. This is Ron again from DJI Enterprise team. And today's video, I'm going to go through the LiDAR data processing using the DJI Terra software. Within DJI Terra software, currently we support the Zenmuse L series LiDAR payloads, including the L1 and L2. And Terra software is a DJI software that is used to get all the raw data captured from the camera system, convert them into a standard formatted point cloud file, among with other deliverable files such as contour lines, such as TIM model, and more. If you are a L1 user, you actually don't need to have a paid license for DJI Terra software to output results in LAS format and convert the coordinate system of your output. Now, if you want to use other functionalities, you will need to have a pro license or electricity license to unlock the additional functionalities. However, if you are an L2 user, functionalities are all free. So that means you don't need to have a paid license to utilize all the related LiDAR processing features within Terra software. Okay, with that being clarified, let's get started and talk about the workflow. First of all, for today's video, I have prepared one data set. So this data set was captured by the L2, and as you can see, I have the data set stored within a folder, and I will be using this data set for today's demo. I have purposely removed all the images. This is because I want to speed up the process. For your daily process needs, you can definitely include these photos as they will be used to colorize your point cloud. And if we're having a closer look at the raw data folder, these files contain multiple raw data coming from different system components. Terra software would utilize them all to compile the point cloud file after the process. Let's have a look at this file specifically, which is a file with a suffix RTB. You should be able to have this file within your raw data folder. If you don't see this file, then this will be an indication that you flew your drone under GPS only and not RTK. And to be noted, DJI Terra software will need to have a base station observation file in order to get the raw dataset processed. RTB stands for RTK base station file, which gets automatically generated when your drone was flown under RTK network. If you plan to use PPK method or post-process kinematic method to post-process your data, you will need to include an additional base station observation file elsewhere in order for Terra software to process the dataset properly. I would show everyone what that process is going to be like with PPK method afterwards. But for this example specifically, I flew the drone under RTK network. That's why you see this RTB file gets generated automatically after the flight. It is important to make sure all these files are not tampered, as when you're transferring these files between different storage devices or even to the cloud storage, it may get compressed or renamed. Please make sure not to rename or change the suffix for these files unless you know what you're doing. If you want to learn more about the file structure as well as to know what these files are specifically, you can refer to our sensor user manual for more detailed information. Okay, let's go back. And as you can see, in addition to the raw data folder, I also have included an Excel file which contains some known points, which I'll be using these known points for controls and checks. In total, I have 10 known points within this Excel file, and I'm planning to use 5 of them as ground control points and 5 of them as checkpoints to verify the accuracy of my system. These known points were recorded under NAD83 2011 geographic coordinate system, so the coordinate format is in longitude, latitude, and altitude. To apply known points into DJI Terra software, you don't have to have your coordinate system written in geographic. If your known points are in projection system with XYZ format, you can also import them in the DJI Terra software. But make sure you know which coordinate system you are using to capture these known points. Okay, with that being said, let's get started creating our sample project within DJI Terra software. After you open the DJI Terra software, on the upper left corner, make sure you're under reconstruction. And the bottom left corner, select new mission. You would find an option called the LiDAR point cloud. Select that and give your mission a name. Select OK to confirm, and that will create a project within DJI Terra software. If you have previously watched my video on photogrammetry data process, you will find the following settings and steps similar. First of all, under Files, expand that and select Folder to import your raw data folder. After data gets imported, you would find this dot in the middle, which is not where you flew the drone, but where the base station was located when you flew the drone. So this is the location of your base station. In fact, you can actually modify the base station center point. So you will find this option called Base Station Center Point Settings. Select this gear icon to modify your base station location. You can change the longitude, latitude, and altitude. Also define the coordinate system used. You may be curious of why we have such option. This is because some users prefer to shift the base station coordinates after they conduct the flight, which is PPK processing. If you have configured your base station and offset from the known point to the center face of the antenna before your RTK flight, you do not need to change this. If you did not apply the rod height and offset the base station location while you're on the site, you will need to do this afterwards. And this will be the setting window for you to apply that. For today's video example, I have only imported one dataset or one flight. If you have multiple flights imported, you would find there are multiple center point settings you can modify. Correctly modify your center point coordinates ensures the absolute accuracy of your data. After you have modified the coordinate, select Save to confirm the settings. For this example specifically, I was using the state-owned course reference station, and such station was using NAD 83 2011. So within this setting page, I would need to modify that to NAD 83 and 2011. And because this is a course base station, which is stationary, I don't actually need to change the center point. And I'm gonna select Save to confirm my data input. Next, we're gonna step into parameter settings. So I'm going to expand this setting page. First setting is going to be scenario. And we have 3 scenarios for you to select from. One is the point cloud processing, LiDAR calibration, and substation reconstruction option. If you like to process out your results, select point cloud processing. You only need to use the LiDAR calibration option when you're experiencing ghosting effect with colorization. It is recommended to perform a task with given settings and collect the raw data with requirements. For a detailed procedure, please refer to our product white paper. And the third scenario we have is substation reconstruction option. This scenario specifically optimizes the visualization output for the substation scene. As you may know that capturing small structure details with LiDAR units could be very difficult. That's why we have created this substation reconstruction scene to allow users to take the LiDAR point cloud data and generate out a meshed model. By doing this, we can preserve the detailed texture captured from the raw photo and apply them back to the model. So these are the scenario settings. Next, we're gonna go to point cloud settings. First of all, you need to define your output formats. By default, we have LAS format checked. You can also check additional formats you want Terra to generate. If you have multiple formats selected, Terra will generate multiple output folders, which contains multiple copies of the data in different formats. And the next, we have merged point cloud output. If you have multiple flights, enabling this feature would merge multiple point cloud outputs into one single output. And then next, I have point cloud density option. By default, we have this setting set to by distance with 20 centimeters, and this means 20 centimeters sampling distance across the whole scan. If you want to reduce that, you can definitely do that. And also by selecting by distance option will give your model a uniform density across the entire scan. Also help reduce the output size. You can also select by percentage, and if you select by percentage, the final output will be sampled based on your setting. And by default is 100%. And this means Terra will output all possible points. Other than the height option, we have medium and low. This will change your density from 100% to 25 and to 6.25%. If you're planning to use a third-party software to further process your data, you may want to keep as many points as you could for the post-process. In such scenario, you may want to consider use the height density option to keep all the points in the output. And the next we have is point cloud effective distance range. Our LiDAR sensor has operation range. If you want to constrain the LiDAR data captured within a given distance range, you can adjust that. But usually this wouldn't be an option we change often. And the next we have is optimize point cloud accuracy, which by default it is turned on. What this feature does is it would take point cloud data within the overlaps region and help adjust and improve the alignment between multiple data strips. This is recommended to be turned on. However, if you're planning to do post-processing work with third-party software, we recommend to turn this off, as some third-party software, they may have strip alignment functionality built in for doing similar work. And the next one we have is smooth point cloud settings. And this option is default off. I do not recommend to turn this option on unless your scanning scene is extremely flat and has no vegetation, because turning this option on would flatten out any small elevation change within 5 centimeters. So unless you're scanning highway or concrete flat surfaces, I wouldn't recommend to turn this on. And that's all the settings within the point cloud settings. Next, we're going to talk about ground point classification. And for the ground point classification, we do want to make sure that we spend little time to adjust and fine-tune the settings in order to get the final classification results accurately. And we need to make sure our classification is accurately done, because the upcoming settings, including the digital elevation model, including the contour lines, these deliverables, they all depend on the ground points, which gets classified in this stage. Let's have a look at the first option, which is the ground type. Within the ground type options, we have flat ground, gentle slope, and steep slope. These are the setting profiles you can apply based on the environment. But obviously, a single profile may not apply to the entire scan perfectly. So at this stage, it is important to verify the ground classification results and make sure the algorithm did not misclassify within your region of interest. Next we have is the building max diagonal. To prevent the algorithm to misclassify the roof of the building as ground, you will need to input the maximum building diagonal to filter out large building roofs from the ground points. This setting is default to 20 meters. If you have a large warehouse, for example, you may want to increase that. And within DJI Terra software, you can do measurement directly, utilizing the measurement tool up here. And the next we have is iteration angle and iteration distance. The iteration angle and iteration distance is basically how the algorithm is able to identify and classify what is the ground point, what is not. Adjusting the ground type would change these two settings correspondingly, but you can also manually adjust these settings. Okay, after we have adjusted the ground point classification settings, the step I prefer to do is start the process and visually examine it and make sure your classification is done properly. This is my preference workflow, as the following outputs and settings are all gonna based on the ground point data. So we want to make sure our ground points are accurate. This process may take a while, so I'm going to fast forward to the end. Okay, so now the process is finished. We can select OK to have a look at the final result. As you can see, everything is white under RGB layer. This is because I have no photos. If you have all the photos imported along with your LiDAR data, this will be colorized. Now let's go to reflectivity, height, and return, these are going to be colorized based on different data field. But now let's select type, and as you can see on the left side, we have point not classified and ground points. So everything here in orange will be our ground points. As you can see, the classification worked done pretty well. We can see all the artificial structures, including vehicles, buildings, vegetation, power lines. They are all classified as not ground points. And on the right side, we actually have an option to filter out not ground points. So just have a look at the ground points. As you can see, in general, we're able to get the ground classified pretty well, but there are a few areas, including this building roof, that got misclassified. So what we're gonna do is further adjust the settings by inputting the building max diagonal. I believe this one is over 20 meters, that's why it's giving me this arrow. So what I can do is select measurement tool and select a distance and measure the diagonal distance between this building. And as we see, the measurement here is 36.28 meters. So over here, I'm going to apply that number to here. So I'm going to apply 36.5 meters and start process. And after this process is finished, we should be able to get the results correctly classified. And again, I would fast forward this part. Okay, so the reconstruction is finished again. Let's select OK to have a look. Now we select type. As you can see, now that roof is being classified correctly. And overall, everything looks correct, no misclassification, and everything is good to go. Last check is to enable the filter again, just to have a look at our bare ground. Make sure there's nothing abnormal. You may find there's a misclassification toward the edge. That is totally fine here because we're not going to be using that area. After this process, we can start looking into the other settings moving forward. I'm gonna close this settings temporarily and expand the digital elevation model settings. Over here, if you enable this option, it will generate a digital elevation model in a GeoTIFF format. And here we have two settings, which is by scale and by GSD. This is change the resolution or the size of your digital elevation model. If you select by scale, we have other settings as well, but generally we would do 1/500, which is by serving standard, or you can adjust the ground sapling distance to make your digital elevation model bigger with high resolution. In this specific application, I'm going to select by scale. And the next setting we have is contour line. So if we expand this and enable this option, there are a few settings here for you to adjust the contour line settings. First is by interval. This is the elevation interval you can adjust. For example, if we set that to 1, this will generate a contour line every 1 meter in elevation. You can also adjust the datum. That's an option as well. But if you don't want to change or shift the datum, for the contour line output, you can leave this as 0 meters. And the next one we have is elevation annotation radius, which default is 15 meters. What this does is it will generate elevation readout for every 15 meters across the scan. And the file will be in Excel after the process. You can also discard invalid contour lines. For example, if the line is too short, you can discard them. Next, let's expand the advanced settings over here. And this is where we input the accuracy control and apply ground points and checkpoints. We're gonna get into these settings. Again, if you have previously watched my photogrammetry process video, this process is actually pretty similar. What we're gonna do is first expand the coordinate system settings and define the coordinate system you used to capture these known points. So what I'm gonna do is adjust the horizontal datum to 8083 2011, select confirm, and change my geoid settings to default, well, because I captured everything in ellipsoidal height. And next, what I'm gonna do is start importing that Excel file I showed you all earlier by selecting this import file option and go back to my directory and select this Excel sheet I have. Select Open to confirm. And I am going to define my data column. So the first column is my name. This one is my latitude and my longitude and altitude. Now the Excel sheet or the data you have for your known points may not be as the same as my format, but you can define the data column and skip rows with the file format settings. So after I have applied longitude, latitude, altitude, the Terra settings will give me data import normal prompt stating everything is recognized. I am going to select import to load all the known points. As every single known points got imported, I can actually see they all got defined as ground control points, but I don't want to use all of them as my controls. I want to use some of these points as checkpoints. So what I'm going to do is I'm going to select these checkpoint files by holding Shift and click the last one and define their type to check. And that would change their icon as well, so I can visually have a look of my known points and make sure they're on the ground. Yeah, and everything looks good. Next, what I'm going to do is do the start processing and select OK to apply these ground control points and checkpoints. After this gets processed, we can have a look at the accuracy report to confirm our results. Keep in mind when placing out known points for your LiDAR data, make sure it's not covered by any vegetations above, as those points above the surface could be misrecognized and applied to the ground point. You want to make sure to place out your control points in an area that is relatively opened. Okay, as this is processing, I would fast forward again. Now that process is finished, so let's have a look at the result. Go to Quality Report option, click on that, and that will bring up the quality report. So this is the quality report for the LiDAR data process. It contains the aircraft data collection time as well as the process time. And if we keep scrolling down, you will find the reconstruction parameters. These are the parameters of Terra software, including the settings you have applied to this project before the actual process. And if we keep scrolling down, you will find the mission parameters, which includes the sensor you are using as well as the sensor parameters when you capture the data. Keep scrolling down, you will find the accuracy parameters, and this is something we should be having a look. The post status indicates whether your drone position is under fixed after the corrections. This applies to both PPK process and RTK process. You should expecting 100% fixed. If you're seeing not 100% fixed or you have some percentage of the flight that is under other, this means you either lost your RTK connection doing the data collection or something is not doing right. So when that happens, I would recommend to use the PPK method to reprocess the data to ensure the global accuracy is good. Keep scrolling down, you would find the point cloud checkpoint arrow as well as the point cloud control point arrow. Now these arrows apply to the vertical axis. So these are all the elevation arrows. So you should be able to find the elevation difference in average from the checkpoint arrow list. And this shows you the average elevation difference as well as the root mean square and the standard deviation. Same thing for the ground control as well. As you can see, we have applied 5 control points as well as 5 checkpoints here, and each individual readings are listed here for you to review. Scrolling down, you will find the digital elevation model arrow as well as digital elevation model checklist. And if we keep scrolling down, you will find the digital elevation model preview. You will also find the contour lines listed here for you to preview. And that's pretty much it. On the bottom, you'll find the output list, including all the deliverables you have preset for Terra to output. You can export this quality report out as a PDF file by clicking on this option. Now let's close the window and exit out the accuracy control and checkpoint and keep going to the next settings, which is our output coordinate systems. So the output coordinate system allows you to convert and transform your deliverables into a desired coordinate system. So over here we have a library of coordinate systems allow you to select from. We have geodetic coordinate system or geographic coordinate system. We have projected coordinate system. So it depends on where your project is located and what the requirement is. You can simply search your coordinate system in the search box or directly type in the EPSG code to quickly jump to the coordinate system you want to apply. And similarly for the geoid and elevation coordinate system as well. Over here we have an option to offset the height. So if you want to, you can also apply that average elevation arrow you are getting to these options to compensate that average arrow to slightly improve the global accuracy of your data. And of course, under applications, you can do annotations and measurements as we covered in the photogrammetry video. That is everything about DJI Terra LiDAR data processing part. Once we have finished the process, exit out the project and go to the project folder by selecting this icon over here. This will bring up the Windows Explorer, and you should be able to find all your deliverables under LiDAR's folder. And as you can see, we have Terra underlined contour, that's your contour line files. If you click on that, as you can see, it generates the DXF and the SHP, as well as that elevation notes Excel sheet for you. In terms of a digital elevation model, we have projection, and we have true world file, as well as GeoTIFF format elevation. Now, if we exit out, and we can also find the LAS file here, because we only have one flight, that's why we have one LAS file. This LAS file contains that classification result. So let's say if you import this LAS file into GIS software, you can actually pull that ground classification result in third-party software. And we have PNTS for visualization. And on the bottom here, we also have sbet.out. This is the projection file for our sensor. You can apply this trajectory file to a third-party software to further process your LAS data. That's everything about processing. Next part, I like to talk about PBK process. As I mentioned earlier within today's video, you can actually do PBK process directly with the Terra software. I actually made a detailed blog on how to do PBK process with DJI Terra software on LiDAR data processing. So I would post the link in the description for you to access that. But let's have a look at the raw data folder again. And let's assume we flew this drone and captured the data under GPS only. In that case, we wouldn't have the RTB file. So let me manually delete this file. And when I delete that file without the PBK observation file, I wouldn't able to get this sample data set processed. Actually, I'm just gonna give it a try to show you what that looks like. So I'm creating a new project and select that same data folder. Now I should be getting an error, as you can see, missing certain data. Now, in order to obtain the base station observation data, there are actually multiple methods for doing that. If you did not have a GNSS receiver to record such data, a good place to start looking to is the National Course Network. So I am going to open up the NGS Course Network. So this is a database that is publicly available, and I'm using the official UFCORS or user-friendly CORS portal to get access with the observation files, which were from the course reference station. So first thing first, we're gonna select the course map to identify the closest referenced station around your project. The easiest way would be search your address or the location of your operation. Okay. Then try to find if there's a nearby station around. Ideally, we want to make sure there's a station within 15 kilometers. So over here on their website, they have measurement tool that you can do a linear measurement. So I'm gonna change that unit to kilometers and do the linear measurement. So as you can see, it's about 8.8 kilometers, which is good. Within 15 kilometers, so I am going to be using the data coming from this reference station, which is called VDCY. That is the code name for this station. So going back to the CORS or UFCORS website, I am going to select that site ID, VDCY, and apply that. And select my operation date. To know the operation date, you can go back to the raw data, and the naming of the raw data should tell you when the data was captured. For example, this one was captured on August 30th. So going back to the website, I am going to select 30th and apply my start time and my time zone. Usually I do 24 hours, so that way I have enough duration to cover my drone flight. And I'm going to select GPS with GLONASS and check the coordinate file, and then select get course data file. And once I do that, the website will compile all the files I need and zip them and start automatically download that file. Once the file is downloaded, let's select the open files. And you should be able to find there are multiple files over here. What you're gonna select is the suffix with 24. 24 is the year of 2024. So O stands for observation. Usually it's the largest size within this zip file. So what we're gonna do is we're gonna extract out that file and make sure to put that file into that raw data folder like this. And what we're gonna do next is to change the name of this file and match with the other files. Usually I would use the LDR because that's our raw point cloud file, and I will use the name of that. Just directly copy that name and rename our 24.0 file. And we're gonna change the suffix from 24.0 or year 0 file to OBS, stands for observation, and hit enter to modify that. And as you can see, I have changed the suffix as well as the name of that file to this one now. I can now close the window, and within Terra software, I can now re-import that same folder, which now contains the OBS instead of RTB, and Terra would load that. You would find that the OBS file I have matched with the RTK because I was using this same reference station for my RTK flight. Okay, with that being said, that's everything about today's video on how to get a LiDAR data project processed within DJI Terra software. I will see you in the next one.